Welcome back, chemistry fans. Tonight, what we are going to talk about is Unit 7, Topic 3. This is going to talk about lattice energy. So let's jump into it right now and see what we can make heads or tails about. So lattice energy, what is it? It's not lattice energy. It's the amount of energy that is required to break apart a crystal and turn it into the individual components of that crystal on the atomic scale. Now, this energy could also be reversed. So it could actually be the amount of energy that it is required to bring those atoms together to make that solid, make that crystal, make that compound. The unique side of this value is that it is the same whichever direction you go. So the amount of energy it takes to break apart the molecule is the same amount of energy that it takes to make the molecule. It's just in the opposite direction. So if it loses energy making the crystal, it is going to require energy to break apart the crystal. All right, so that's our definition for lattice energy, the amount of energy released when a crystal containing 1 mole of an ionic compound is formed from a gaseous ion. And what that means is that it's how much energy it takes to make the crystal. But again, it's also the same amount to break it. It's just in the opposite direction. One of the things to remember there is what we talked about last time. The higher the charge, the stronger the lattice energy is. And the closer the atoms are, the smaller they are, the harder it is to break apart. And you see this on this trend, noticing that as we go down the periodic table from fluorine to bromine, that the atoms are getting further apart, and therefore it is easier to break them apart. Notice that the energy goes down. A similar trend that you might see if we take a look at NaCl, its value is 787. But then if we come across over here, whenever we have a charge of 2, where sodium has a charge of +1, magnesium has a charge of +2, the energy amount escalates significantly. And then if we look at what happens whenever we have an element with a charge of 3, it's much harder to break apart these molecules because their charges are higher and they have more bonds. So this brings to mind something called Coulomb's law. Coulomb's law says that the closer the 2 charges are, the stronger the forces between them. So how do you get them closer? You make them smaller and you make them with multiple bonds. So how do we know if they're smaller? We have a trend that we have learned in the past. It says that up here in the upper right-hand corner that the smallest elements are on the periodic table. If we go look down the bottom left, they are larger. So the larger elements are down on the bottom, the smaller up at the top. So the stronger bonds are going to occur with the elements at the top of this periodic table. So here is that trend. As you go down the periodic table, you notice that their lattice energy starts to decrease. If you are on the higher end of the periodic table, your lattice energy is very high. Summarizing this whole trend here, if we increase the charge, we are increasing the lattice energy. If we increase the size, we are decreasing the lattice energy. But if you go in the opposite direction, which this picture shows, this arrow shows, it's saying the strongest atoms are going to be up in this corner up here where they have the small size and they have the largest charge. Small size, large charge. The weakest held atoms, molecules, are going to be the ones with low charge and large size. So here's the summary of all that information right now. The higher the charge, the stronger the bonds. The smaller the size, the stronger the bonds. But on the opposite side, the lower the charge, the weaker the bonds, the larger the size, the weaker the bonds. All right, let's talk about lattice energy now, finally. How do we calculate it? Have you ever had that moment where you hear stories about people that spend an hour in the morning getting ready before they come to school, that they do not want to set foot anywhere out in the public without having perfect presence? And you see that kind of in this picture. You notice the lady, she's putting on some concealer. She's trying to, she's obviously had makeup. Her hair is done perfectly. And then there's the guy over there. He didn't bother to shave that day. He's just rolling out of bed. He took a shower, maybe, and then he's heading to work. And that's not fair, but that's the way it is in society, is that there are some folks who feel comfortable with with just an honest appearance, and there are some folks who like to make their presence a little bit more elaborate, and they like to care about their hygiene and their efforts. Well, whenever we talk about chemistry, you may not be able to appreciate that same scenario, that there are a lot of steps before you get to school, and there are some other people that just see the final step. So this is called the Born-Haber process. In the Born-Haber process, there are multiple steps before we can actually make crystals. Now, we see it as just a simple process. But this shows here from this image that there are multiple steps to make a compound. It's just that we cannot appreciate all of those steps happening because many of them happen so quickly. So here we go. Here are the steps involved in every process that we are going to try and solve. We must convert descriptions of words into chemical reactions. We need to fix their inconsistencies with respect to the number of atoms. Then we got to simply add it all together to get their sums. So I'm going to show you some examples of that. But before we get to that, some of those words that need to be converted are present here on our slide. We're going to hear terms like heat of sublimation. You're going to have to understand that what that means is the element is converting from a solid into a gas, or vice versa. It could be going from a gas to a solid, but they will use the term heat of sublimation. Ionization energy means that you are losing one electron. Now, they could say the second ionization energy, and what that means is that you've already gotten one electron removed. Now you got to remove a second one, but they will each individually have amounts of energy. Bond energy is just simply, and it doesn't sound logical, but everything in this is going to have some kind of reverse context. Bond energy is separating apart a molecule into its individual elements. And I know that that sounds reversed. Bond energy could also be adding two elements to make the compound. Electron affinity is where you are accepting electrons. So this is the exact opposite of ionization energy. And then the final term that we need to become familiar with is the heat of formation. This is the final step in the process where we are adding together the compounds to make the molecule. Lattice energy might be also lumped in here, and that's where we are making our compounds. So here's an example of what I was talking about. Whenever we have thought about making salt, we've always just shown it as Na plus Cl makes NaCl. We would balance it by putting 2's in. We thought that that may have been challenging. Well, now what we've got to understand is that the reality is all of these materials must be turned into gases before they can react. So the sodium, it must be converted into a gas. And the chlorines, they must be separated into individual atoms. And then the sodium must be turned into an ion. The chlorine must be turned into an ion. And then and only then, whenever we have both of the materials as gases and as ions, can we form the salt crystal. This is what we're talking about. It's more complex than what we expected. And we have to add up then every single one of these energies along the way. And then we can get our sum of this value. So it would be 502 plus 121 plus 107 minus 411 minus 355 minus 786. And what we would come up with is our final answer. There is going to have to be a loss of 822 kilojoules of heat to make 1 mole of salt crystals in the solid form. It's more complex than what we would have expected. So we have to learn how to deal with this. In this next example, what you're going to see is where the trick to the process comes in, because it looks like it's pretty easy mathematically just to add these together. Here is the one hiccup in this process. They will intentionally leave one of the steps with an error built into it. and you have to recognize why there's an error and why you must fix it. Notice, if you will, that in the previous step, chlorine is separated into 2 chlorine atoms. In the next step, we are turning the chlorines into chlorine ions. But this heat, negative 349, is for 1 chlorine. But there are 2 chlorines, so therefore we must multiply the heat by 2. This is the one little hiccup, the wrinkle that comes along with solving for a lattice energy problem. So in this next one, you will notice that it's, again, very straightforward. But instead of solving for the sum, we're solving for what the lattice energy is, the missing value. So what we would do in this case is we would need to look at this total, negative 594.1. And then this becomes just like an algebraic problem. Negative 594.1 equals x plus 155.2 plus 75.3 plus 520 minus 328. Now, do we see any portion of this that needs to have a correction? Fortunately for us, with the lattice energy, they took care of it for us. So we don't need to double this by multiplying it by 2, because in the next step, they actually made it only for 1 of the F's. So they took care of that in this problem, but we're still going to solve for the mathematics of this one. So negative 594.1, and then we're going to solve for this X. So what I'm going to do for this is I am going to simply subtract all of these values so that they cancel out and they go over to the other side. So I've got negative 591.1 minus 155.2 minus 75.3 minus 520 plus 328. And what you end up with is a negative 1016.6 kilojoules of heat. So that's my answer for the lattice energy. How much energy it took to create those crystals. All right, here's our chance to solve one by ourselves. So here's our example. We are looking for the total heat. How do I know that? Because of the symbol up here. It's saying the total heat. Now let's take a look and make sure that there's not somewhere where there needs to be a correction. Look at the third step down here. Notice that there are 2 BRs. In the step below it, there's only 1 BR. That means that this entire step needs to be multiplied by 2. Now we've gotten everything that we need to solve this. So let's go ahead and add together our values, sum all of these together with our new correction, and we will get the right answer. 89.24 plus 419 plus 193 minus 325 times 2. Minus 394. And what you'll notice about this answer, negative 342.76 kilojoules of heat. That is our answer for this one. I got one more example that I want to work with you for our lattice energy examples. So let's see what we can do here. Same process. We are solving for the heat. Do we see anywhere that we need to make corrections? I do. Notice here that this is for 2 bromines, but the next step only has 1 bromine. We again need to multiply by 2 to make this work out. So I'm going to take 329.1 plus 577.6 plus 1816.6 plus 2744.7 plus 193 minus 325 minus 325 minus 527.2, and it ends up, this value is much larger as a positive value, positive 4,483.8 kilojoules. That is how much heat it took to make a molecule of aluminum bromide. Okay, this is everything that I wish to share with you today about this problem. So I thank you very much for your time, and I'm going to turn this off, and we will talk again soon in class. Thank you. Bye-bye.